Hello, welcome to the RevitalVision Science presentation. My name is Shlomo Abramson. I'm a certified optometrist and the clinical service manager at RevitalVision. This presentation covers RevitalVision Science and its unique mechanism of action. Let's get started. So the quality of the image we see depends on both image capturing and image processing. RevitalVision focuses only on optimizing the brain's visual processing. RevitalVision does not affect refraction or accommodation. This was ruled out in randomized controlled studies. RevitalVision Science is based on four building blocks: Gabor patch, neuronal lateral interactions, brain plasticity, and perceptual learning. The first is the Gabor patches. This holographic image is considered to be the most effective visual stimulation. If we try to visually stimulate the cortex and measure the neural response, the Gabor patch will induce the highest response of all other images. The reason for this is because the shape of it perfectly matches the shape of the neuron's receptive field in the primary visual cortex. The Gabor patch was discovered by Dennis Gabor, a Nobel Prize winner in physics who discovered the hologram. Both the hologram and the Gabor patch are described by a complex mathematical formulation. RevitalVision software uses a drawing engine that uses this mathematical formulation to accurately draw the Gabor patches on the patient's computer screen. Stimulating the visual cortex with Gabor patches alone will not improve vision. The stimulation has to be done in a very specific way. The second scientific building block is based on the famous cat visual cortex experiment of Hubel and Wiesel from 1959. The scientists anesthetized a cat and inserted a microelectrode to its visual cortex and connected it to an amplifier. In a dark room, they projected a light on the screen in front of the cat's open eye and measured the response of a single cell. They discovered a phenomenon that later awarded them with a Nobel Prize in medicine. They found that a single neuron in the primary visual cortex is sensitive and responds only to one type of visual stimulation based on three main parameters: the location of the stimulation within the visual field, the orientation, and the spatial frequency. In this example, we see a horizontal stimulus. Only neurons that are sensitive to process this specific type of visual stimulation will react and interact with other neurons of the same type. To characterize an image, visual processing involves the cooperative activity of many neurons. The neural response to the stimulus can be facilitated or suppressed by other stimulus falling outside the receptive field, which when presented in isolation fail to activate the cell. So the flankers can create a crowding effect, suppressing the neural response, or an inducement effect, enhancing the neural response, depending on specific parameters. 40 years following the cat visual cortex experiment, Uri Polat, an Israeli scientist, replicated the same study setup, but this time replacing the projected light with Gabor patches. In the first part of the experiment, he measured the cortical response to a single target Gabor image and found linear correlation between contrast and response. In the second part of the experiment, he added two side flankers to the target Gabor and found that in certain parameters, the flankers can facilitate and enhance the neural response, while in other parameters, they suppress the response. Here, the green line demonstrates the neural response to a single target Gabor, and the blue line demonstrates the response to the three Gabor images, which is the target plus the flankers. As you can see, there is a significant increase in neural response in a certain area. This slide further explains the previous one. The red column represents the neural response to a single target Gabor. The middle demonstrates suppression or lack of neural response in the case of flankers alone, and the strong response facilitation to the triple Gabor image, targets and flankers. Facilitation happens in very specific parameters only. If we increase the distance between the flankers and the target, at a certain distance, there will be suppression. It also depends on the orientation and the contrast relation between the target and the flankers. The highest neural response happens when the target Gabor is at a very low contrast at the edge of vision in the presence of two flankers at a higher contrast. During the training session, the software trains the patient at the edge of his or her vision to achieve a high neural response. RevitalVision's main intellectual property are proprietary algorithms that calculate these parameters to tailor a high neural response to each individual patient. Neural plasticity relates to the ability of the nervous system to adapt to change conditions in acquiring new skills, and the newly acquired skills are retained for years. Up to the 1950s, the adult brain was thought to be hardwired with fixed and immutable neuronal circuits. Evidence for neural plasticity, visual acuity improvement in adults with amblyopia, has been reported and documented after prolonged patching, or when the better eye's vision has been lost or degraded by age-related macular degeneration, cataracts, or trauma. Interestingly, these cases were mostly reported as case reports representing an unusual phenomenon. In order to understand the prevalence of neuroplasticity in adults, we should look at large data. Large randomized controlled trial and meta-analysis studies demonstrate very limited vision improvement in amblyopes older than 11 years old, even with prolonged patching and after loss of vision in the non-amblyopic eye. Perceptual learning is RevitalVision's fourth scientific pillar. Perceptual learning is a process in which the ability of sensory systems to respond to stimuli is improved through experience. Perception can be modified by experience, and visual performance improves with practice. Perceptual learning has been evidenced in a variety of visual tasks and was found to persist for years without further practice. Clinical observations and experimental evidence indicate the presence of residual neural plasticity well after the critical period. However, general stimulation with patching in adults has very limited effectiveness. In order to effectively stimulate an adult visual cortex and improve the vision, there's the need for patient-specific visual stimulation, conducted in a controlled and repetitive manner using perceptual learning technique. How does RevitalVision use perceptual learning to improve vision? RevitalVision enhances neuronal lateral interactions using the unique lateral masking technique. The patient is exposed to a very strong stimulus, the 3 Gabor images, in a repetitive manner. The high stimulus triggers high neural response and gradually trains the neurons to be more responsive to the visual stimulation and to form new connections among these neurons. The repetitive stimulation increases the neural detection point and reduces the surrounding neural noise level, leading to improvement of contrast sensitivity function by reducing the noise to signal ratio of neural activity in the primary visual cortex. This improved contrast sensitivity function induces improvement in visual acuity, and the better balanced visual acuity induces stereo acuity and binocular functions. To summarize RevitalVision Science, neurons in the primary visual cortex respond only to one type of visual stimulation based on location, orientation, and spatial frequency. RevitalVision software identifies the patient-specific cortical deficits, neurons that do not respond well to specific visual stimulation based on threshold detection tasks. Then the algorithm tailors a specific stimulation program to match specific cortical deficits and patients' needs. The software uses Gabor patches with lateral masking technique, achieving extreme neural response. And then the repetitive strong neural responses form neural connections at the synapse level. In the next 4 slides, I will explain how RevitalVision Science was transformed into technology. Patients are presented with a series of visual stimulation using Gabor patches in different parameters, dynamically controlled. Here are examples of the different visual stimulation the software uses. As we learned from the cat visual cortex experiment, a single neuron in the visual cortex is sensitive and processes only one type of visual information. The software needs to measure and stimulate all the different groups of neurons in the visual cortex, and therefore uses different types of stimulation like spatial frequency, location, and orientation to target the different groups. Here's an example of a visual perception task, the triple image task. The patient is exposed to two short displays in succession in a random order. The patient needs to identify which display contains 3 Gabors. If it was on the first display, the patient should click the left mouse button, number 1. If it was on the second display, the patient should click the right mouse button, number 2. The system provides the patient with feedback in case of an incorrect response. The task is repeated and a staircase is applied until the patient reaches their visual threshold level. The software will measure the threshold several times to overcome the patient's ability to guess the correct answer. Once the software identifies consistent answers to a specific task, it records the specific threshold and moves to the next visual task to measure the function of a different neuron type. The first 2 sessions are computerized evaluation sessions in which the software maps the patient's complete neural sensitivities and deficits. Following this mapping, the software tailors specific visual stimulation program to address these deficits and sensitivities. Let's take a meridian amblyopic patient, for example. Born with astigmatism, the image that was transferred from the retina to the brain was blurry at the degree of the astigmatism. The neurons responsible for processing this degree of astigmatism were lacking effective stimulation during the critical age, and a meridian cortical deficit was formed. During the 2 computerized evaluations, the software will detect poor performance to the visual task in the degree of the astigmatism and will focus on stimulating these neurons. What makes RevitalVision so effective in comparison to patching and other digital solutions for adult amblyopia? We have 3 key advantages. Number 1, the level of stimulation. Using the lateral masking technique, it induces extreme neural response. Number 2, the ability to tailor specific stimulation to match the specific cortical deficits. And number 3, the ability to stimulate specific patients at specific effective contrast levels. In order to induce a high neural response, the software needs to display the Gabor patch at very low contrast at the edge of his or her vision. Stimulating at high contrast was found ineffective in controlled randomized trials. Thank you. This concludes the scientific presentation. All the best.